Hi everybody, it's good to see you today. Hope you're all safe and well. We're moving into Chapter 5 of the Math 71 program. And Chapter 5 involves two major objectives. Objective number 1 is to take a look at the characteristics of polynomials, and then we will be operating with polynomials in terms of adding, subtracting, and multiplying them. And then in the second half of Chapter 5, we'll be doing the inverse of multiplying polynomials, and that will be factoring polynomials. And we'll look at all of the techniques of factoring polynomials, and then we'll end Chapter 5 with solving quadratic equations by factoring, and then we'll be looking at some specific application problems that deal with quadratic equations. Now, we've already looked at a couple of videos involving 5.1. And in 5.1, we are taking a look at some of the key characteristics of polynomials, specifically key vocabulary pertaining to polynomials. And then we have taken care of a video that deals with adding and subtracting of polynomials. In this video, we're going to be looking at a specific content area that is involving polynomial functions and their graphs, and specifically pertaining to the graphs of polynomial functions, we're going to be looking at the concept of the end behavior of polynomial functions. So I want to come up to this whiteboard right here, and we want to speak to some key thoughts that are going to lead us to being able to determine what's commonly referred to as the end behavior of the graphs of polynomial functions. So I just kind of want to start off with the idea of a polynomial function. We have thoroughly defined functions and talked about domain and range and have done already quite a number of things with functions. But a quick definition. A polynomial function is very simply a function that is defined by a polynomial expression. So this one right here, read in the following way. The value of function f when the domain is x is equal to the range of x squared minus 5x plus 6. And people, that range of x squared minus 5x plus 6 is a polynomial, specifically a trinomial. So a polynomial function is a function that is defined by a polynomial expression. The second one, the value of function g when the domain is x is equal to the range value of x cubed plus 3x squared minus x minus 3. It's been defined by a polynomial that has 4 terms. Now, it just so happens that the graph of this polynomial function right here happens to be this curved, bowl-shaped curve that is opening upward at both ends. You are probably well aware of the fact that it is called a parabola. That's not so important necessarily right now, but having had mathematics prior to this particular course, you're probably aware of that vocabulary term. I apologize a bit. I am no artist. This is not the best sketch of what a parabola would look like, but it's going to have to do for our purposes right here. This happens to be a pretty close resemblance graph to this polynomial function that is listed right above it. And this happens on this area of this coordinate plane, happens to be another view of another parabola that happens to be opening downward as opposed to the one that truly exemplified this function right here that happens to be opening upward. You'll notice that the end behavior on the far right and on the far left of this graph, the end behavior happens to be the same on both the right and the left of the graph. It's opening upward to the right, and it's opening upward to the left. It's rising to the right, and it's rising to the left. We'll have more to say about this in a moment, but we can say right now the end behavior for both the right-hand side and the left-hand side are the same. They have the same behavior. It's rising to the right, and it's rising to the left. On this one, it's falling to the right, and it's falling to the left. Over here, for this given polynomial function, this happens to be sort of a replica of the actual graph for this polynomial function here. And I guess the one thing that I kind of want you to see about this graph is, if you look at the far right of the graph, sooner or later we see that this graph is rising to the right. And it's going to keep going to the right boundlessly. It'll never end. And it'll continue to go up and rise to the right. Whereas the behavior of this graph on the far left has an opposite behavior to what we just described. It happens to be falling on the left. It's falling to the left, and it happens to be rising to the right. There is something to be said about this kind of a graph and its end behavior based on the function that we see up here that we will be talking about. Whereas on this polynomial function right here, the end behaviors are opposite again. But in this particular case, it is rising to the left, and it is falling to the right. Opposite behavior here, opposite behavior here. Now, one thing that we want to state about all graphs of polynomial functions: they are all smooth and they are continuous. What I mean by smooth is all graphs of polynomial functions have rounded corners. There are never sharp corners that are pinpointed in this particular way. They're never sharp, they're rounded, so to speak. Rounded, 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 rounded. Never any sharp corners. And the second characteristic about the graphs, they're continuous. There are no breaks in the graph. There are no separate branches of the graph. It is a continuous looking graph. It's continuous if you are able to plot all of the points, or a whole lot of the points for the given graph, and you were to connect it. You would be able to take your pencil and begin with one point, and you would be able to make the entire graph continuously without lifting your implement up on any of these. It's continuous without bound. those are some of the key characteristics of the graph of a polynomial function. Now, to just interject this thought, the Math 71 program will not expect you to graph polynomial functions, with the exception of one. When we get to Chapter 8, we will graph the parabola, but we will not be graphing any of these kinds of polynomial functions that you see demonstrated up here. They were only up there to bring across a particular point. Now, the key aspect to the polynomial functions, I've already alluded to it right now, but now we're going to pinpoint it. The key characteristic or the key objective of what we want to do with the polynomial functions and their graphs is to speak about end behavior. Now here's what we want to say again about the end behavior of polynomial functions. As the value of x either increases, this is the x-axis, as the value of x either increases or decreases, the graph of every polynomial function will either eventually rise to the right or rise to the left, fall to the right or fall to the left, or rise to the right and fall to the left, or rise to the left and fall to the right. Every single polynomial function, its graph will either rise or it will fall as x increases or as the value of x decreases. Now, the end behavior of a polynomial function can be determined without actually looking at the graph. You are not necessarily going to be looking at graphs. I showed them to you at the beginning, but on the examples that we're going to be looking at, zeroing in on end behavior, you're not going to be seeing graphs. You're going to be seeing the literal function. And when you look at the literal function, there is a test that can be done to determine the end behavior of the graphs of that particular function that we would be looking at. And so here is the lead up to the test that is going to be done that will determine the end behavior of the graph of a polynomial function. It has to do with some key vocabulary that would have already been spoken about in an earlier video of Chapter 5, and that has to do with degree. So we're going to kind of talk at the beginning here and get it down to the critical rule that we're going to be following. Let me just back up all the way to the beginning and let's talk about the degree of a polynomial. The degree of a polynomial is the greatest degree of any of the terms of the polynomial. I'll say it again. The degree of a polynomial is the greatest degree of any of the terms of the polynomial. Let's come up to this one right here, and Kristen will kind of pinpoint this one. Now this is a polynomial function. Let's look specifically at the polynomial expression. It is a polynomial that contains 4 terms. The degree of a polynomial is the greatest degree of any term that makes up the polynomial. So this is term number 1, term number 2, term number 3, and term number 4. So we're going to identify the degree. of each one of these monomials that make up that polynomial. Now, from a previous video, the degree of a monomial is the sum of the exponents on the variables only. The degree of a monomial is the sum of the exponents on the variables only. So let's start with this first monomial term. The degree of this first monomial term is 3. There are no other variables involved with this term, it's just the variable x. 3 is its degree. In the second monomial term, 2 is its degree. In the third monomial term, the implied exponent is a 1, so its degree is 1. And this last constant term, it has a degree of 0. The greatest degree of any of the terms of that polynomial is 3. So the degree of this polynomial expression would be 3. Now, moving on with this description. The term that identifies the degree is called the leading term of the polynomial. This is the degree that identifies, this is the term that identifies the degree of the polynomial. It has a degree of 3. It's this term that identifies the degree. This term is called the leading term of the polynomial expression. And oftentimes, the leading term is the term right out of the gate. It's ordinarily the very first term of the expression. It doesn't have to be, but it ordinarily is. So x to the third, because it's the term that defines the degree of the polynomial, x to the third is called the leading term. Now, the key test that is going to be handled, that is going to define the end behavior of the graph of a polynomial function, has to do with the lead term of the polynomial expression. And people, 2 specific things about the lead term. Item number 1, what the degree is, the actual degree of that lead term, the actual degree of the polynomial, and secondly, the sign of the coefficient of that lead term. Now let me say that again. The lead term is the key term that's going to lead to the end behavior of the graph of a polynomial function. But within that lead term, there's 2 specific items that we look at that will determine the end behavior of the graph of a polynomial function. One of those things is the exponent, which is going to classify the degree of the polynomial, and secondly, the sign of the coefficient of that lead term. And so, right down here at the bottom, the sign of the coefficient of the leading term and the degree of the polynomial will determine the end behavior of every polynomial function graph. And here are the rules that we're going to follow. Kristen will show this. I hope I have made it as carefully as I can. It's a test that we apply. Just like we applied a vertical line test to determine if the graph of a relation was a function, there is a test that we can do without ever having the graph in front of us, no graph at all. We can apply a test that will determine what the end behavior of a polynomial function will be. It is called the leading coefficient test. The word leading references the fact of the leading term. The coefficient speaks about the coefficient of that leading term. And here is what this leading coefficient test has to say. If the polynomial function has an odd numbered degree, the degree is 3, the degree is 5, the degree is 7. If the degree of the polynomial function or the degree of the polynomial is odd, you look at the leading coefficient. We're always going to be looking at the leading coefficient, but keep in mind we're talking about an odd degree polynomial. If the leading coefficient is positive, the graph will fall to the left and it will rise to the right. If we are looking at an odd degree polynomial, if the leading coefficient is positive, the graph will always fall to the left and it will rise to the right. Now people, this is not an ordered pair, and it obviously is not interval notation. It's just using parentheses, as they oftentimes do, to kind of, using symbols to point out the end behavior of the graph. It'll fall to the left, and it'll rise to the right. If I can have Kristen come right back to this one right here. Look at this polynomial function. It has a degree of 3. People, that's an odd degree. And the coefficient of the lead term is positive. If the lead term is positive, the degree of the polynomial is odd. The graph will rise to the right and fall to the left. And that is exactly what this says. If it's an odd degree polynomial and the leading coefficient is positive, the graph will fall to the left, it fell to the left, and it will rise to the right. Now you're not going to have the picture. We'll have to know the rule. If it's an odd degree polynomial and the leading coefficient is negative, odd degree, negative coefficient, the graph will rise to the left and it will fall to the right. It will rise to the left and it will fall to the right. Over here, if we can just look at this one, okay? I don't know, I don't have the picture, but I can do this. If I were to make this negative, now, please understand, that would not be the graph of him. But let's just use him based on the change that I made here. This is an odd degreed polynomial. It's 3. Its coefficient is negative. What will the end behavior of the graph look like? It will rise to the left and it will fall to the right. Let me make one parting comment about odd degree polynomial functions. If the degree is odd, the graphs of those types of polynomial functions will always have what's referred to as opposite behavior. they'll have opposite behavior. In one case, one will fall to the left and rise to the right, and in another case, it will rise to the left and fall to the right. Odd degree polynomials have opposite behavior in terms of the end behavior of the graphs. Let's go to even degree polynomials. If the degree of the polynomial is even, a degree of 2, a degree of 4, a degree of 6, a degree of 8, the behaviors will be the same. We'll point it out. Even degree polynomials. If the leading coefficient is positive, the graph will rise to the left and it will rise to the right. The behaviors, people, will always be the same if you have an even degree polynomial. If the leading coefficient is positive, the graph will rise to the left and it will rise to the right. Case in point, this parabola right here. It is the graph of this polynomial function. It's actually a quadratic function. Look at the degree. The degree is 2. Even. Coefficient is positive. If the degree is even and the coefficient is positive, the graphs will have the same behavior. It'll rise to the right and it'll rise to the left. And if the leading coefficient for an even degree polynomial is negative, they will have the same behavior. But in this case, the graph will fall to the left and fall to the right. This little puppy right here. Let's just say I change this one. This graph would not be the graph of this one if I changed it to this. But let me just put a negative right there. If he were a negative coefficient with an even degree, it would fall to the right and it would fall to the left. For even degree polynomials, you have same behavior. For odd degree polynomials, you have opposite behavior. Now, 4 little examples here to wind down this video. This is what you are going to be evaluated on. I'm not going to give you a graph. I'm going to give you the function. And we're going to follow the leading coefficient test to determine the end behavior of the graph of each of the polynomial functions. In other words, what the graph would look like based on their end behavior. So let's go to number 1. You find the lead term. Now make no mistake about it, this is not much of a polynomial right here. We've got a binomial. The degree of that term is 2. The degree of this term is 4. The greatest degree of any one of its terms is the degree of 4. Therefore, this is our leading term, a negative 1x to the 4th. The degree is even. Same behavior, people. And the coefficient of this lead term is negative. It's a negative coefficient with an even degreed polynomial. That means their end behaviors are the same. And because the coefficient is negative, all you would need to do is write down something like this. It will fall left and it will fall right. I suppose if you wanted to show something like this, you could. It'll fall left and it will fall right. They have to have the same behavior. Number 2. another binomial expression. That has a degree of 2. He has a degree of 3. He wins. He's the leading term. The degree is odd. Opposite behavior. Odd begins with an O. Opposite behavior begins with an O. The degree is odd. They're going to have opposite behavior. Look at the coefficient. The coefficient is a positive 1. The coefficient is positive with an odd degree. It will fall to the left, and it will rise to the right. It will fall to the left, and it will rise to the right. That's all that you will be doing. You're not going to be seeing the graph. Number 3, polynomial function defined by a trinomial. The degree 0, the degree 1, the degree 2. He wins. Even, same behavior. Coefficient, positive. It's going to be a parabola. They're both going to rise. Rise. Left. Rise. Right. I know it's sloppy, but I'm working off of the wall of a room here, and I don't want any issues. So it's going to rise to the left, and it's going to rise to the right. Last one, polynomial function. You can see he wins. Odd, opposite behavior, negative. Rise, left. Fall, right. Rise left, fall right. That's what that little concept is about that we wanted to take care of and not ignore. It is one of the unique things that 71 has for us that 51 did not. So we wanted to bring that concept across. Now we'll talk again soon as we move forward. You have a good day today, and you keep that smile on that face. Take care of yourself. Bye-bye.